So we would talk about Iceberg and especially PyIceberg today. I work at Confluent and our company created Apache Kafka. And of course, later we have moved on to Kafka and Flink. And now for the last 6 months, we have worked on having Kafka topics as queryable Iceberg tables as well. So normally I do Kafka and Flink, but then for the last 1 year, I'm also talking about the integration between Iceberg and Kafka. So for today's session, what we're going to do is we're going to break down what Iceberg is quickly, and then we would jump into this whole notion of how you could have your Kafka topics as queryable Iceberg tables, and then we would jump into PyIceberg. What's there for a Python data engineer like me in terms of using Iceberg? And then last 15 minutes or 20 minutes, we could have a demo and questions, etc. If you have a laptop and you are connected to internet, you can work with me. It's like a 5 minutes, 2 minute setup. And I've kept the code on GitHub as well. But if you don't have a laptop, just watch along as well, right? Now, a statutory warning. Not a single LLM was harmed in creating this presentation as well as my demo. I tested the demo in the morning, it was working fine, but it might not work as well. So you've got to admit that in this age of AI, imperfections count as well. So I've created this whole presentation keeping in mind, we would break it down into these 3 broad sections, and then of course the demo, right? So we would start with Apache Iceberg from bottoms up, what it is and the whole intuition of having Iceberg and what kind of problems does it solve. So OLAP data platforms or online analytical processing data platforms, if you look at it, it is composed of these basic layers. One is of course storage, where you would keep your data files. Then you had the file formats. So file formats could range from Parquet to ORC to Avro, which are powerful, compressed, sometimes splittable files, which actually lets you pack in a lot of information, not only the data, but also a lot of metadata, which helps in running queries very fast. And then of course we have this layer called table format. Now, Iceberg is an open table format, but table format is nothing new. So what I am showing here actually exists within an RDBMS as well. Or let's say, which is an OLTP, or let's say within a legacy old warehouse as well, right? So you would all have a storage engine, you'll have the files, you'll have an open table format which helps you do your data manipulations, right? DMLs, create, read, update, delete. Then you would have a storage engine which lets you pack your files properly, index those files, and then you would have your query engines, right? And you would have a catalog, which would have a dictionary, data dictionary, or metadata about the data which is stored. Now, this is true for all data platforms, be it a RDBMS, be it a OLAP, so it doesn't really change much. The thing is, with old data warehouses, what happened was all these were packed up in one single black box. So compute, storage, table formats, file formats, you do not really have a lot of options in terms of going to each of these layers and do your own stuff, right? Now, data lake came in, let's say late 2010s, 2017, 16, 18, 19. And what it did change was it opened up this storage to have data of all different sorts. So you could have structured data, unstructured data, images, files, and whatnot. But then the thing that a lake lacked was the storage engine was still proprietary, number one. And number two, it was not DML capable. So you could not write an update. Or if you're doing data warehousing, you would know this merge or upserts. So you have a lot of data historical and then daily data come in, which is incremental, and you merge these records. So it's a very common syntax, right? So when you do a merge, you write a merge or an upsert on these tables, and then just do if matched, then do an update. If not matched, do an insert. And I don't think it functionally changes for any warehouse, to be honest. Now, what the Open Lakehouse did was opened up all these layers into something which is commonly known as composable data platform. So you could actually have different things coming in each layer, which is open, and you could choose depending on your needs. So the evolution, if you look at it, is something like this. So if you look at it, you would have those open query engines or proprietary query engines, from only proprietary query engines. And if you look at this slide, you would understand that I could have my storage locally on my disk in a VM. I could have it on HDFS on a VM, on a bare metal if you wish. I could have it on cloud storage as well if you want. And then the file format, I have options. I could have Parquet, I could have Avro. Open table format, well, there are 3 really, but today I would only talk about Iceberg, and I've just mentioned Delta Lake because it's a competitor to Iceberg. And then you have storage engines, you have query engines. You could bring in your own query engines like Trino and Spark and Daft and DuckDB and whatnot. And then you have a choice of catalogs as well. There are many open source catalogs today. You have Nessie, you have Gravitino. Iceberg has written the spec or the specification for a REST catalog, which you could use as well. And then you have the proprietary catalogs as well. You have AWS Glue, Polaris is open source. Then you have Unity from Databricks. It used to be proprietary, now they have open source it as well. So the point that I'm trying to make is it has become composable. So you could have your own layers. Now, how does that impact me as a data engineer? I'm a Python data engineer. How does that impact me? So for one, in a data lake, since I don't have insert, update, delete capability, if there is a change, if I want to merge, I would need to create a whole separate folders for that, right? That's gone. I could do DML operations right on the data. We'll go into the mechanics of it, how it actually happens. And then, of course, it lets you do all these sophisticated things like a time travel. Based on a timestamp, you could actually go back and figure out what was the data state before all these updates took place. Can you do it in a data lake? You can, but then it would require keeping a lot of different copies of the data itself. But with Iceberg, what happens, or with open table formats, the copy is only done on metadata and not the real data. We'll come to that. It's open architecture, etc. So the goal remains threefold: to have DML capability, to have time travel so that I could go back in time, and then have proper ACID kind of a semantics so that I could implement this optimistic concurrency control, etc. Right? So essentially, again, going back to the same analogy, what does a table format do? A table format treats data files as tables. I have my incremental files coming in every day, or I have my historical data that I want to analyze, on which I would eventually maybe create BI reports or pass it across to the AI team to create their own stuff, etc. But fundamentally, what it does is it treats data files as tables. Now, Apache Hive actually took this to this abstraction back in the days like 10, 12 years back, 15 years back actually, when it let you query read-only, in a read-only way, only select, on data files, homogeneous data files kept in folders. So you could have one folder, and that could appear in Apache Hive Metastore as one table. So just if you already know, you know it. If you're new, just take this pause and just think about it. You have one folder with a lot of new files every day coming in, but it's all homogeneous, and I expose that as a table so that I could write SQL queries on top of it. And Apache Hive was the first project which did it. Extremely popular even today. This Hive metastore powered by Apache Hive. The catalog you could build on top of almost everything. You could have it on JDBC. You could have your own. But the whole point was, if you look at it, I have this directory called db1/table1. Within the directory, I could have this data for every month, and I could write month equal to 01, one folder, month equal to 02, another folder, and then I could just push all these data files in, and my SQL query, I could write those predicates where I only want data from month equal to 1, and only the first set of data files would be scanned. I think phenomenal concept in terms of creating a data warehouse and running SQL queries, right? Hive metastore. It also gave you properties like you could do partitioning on a field, it could be a timestamp, it could be something else. The querying was file format agnostic, so you could have Parquet, you could have CSV, and then of course you could take full directory, copy it to another directory, which is called an atomic swap, by the way, and then you could invoke queries on the new directory as well. All was possible through Apache Hive, right? But the problem was it was still directories. And that was one of the fundamental reasons why you could not do a DML operation on top of it. You could not do an insert, update, and delete, right? Because the metadata knew only at the directory level what my table was, but not at the file level. So fundamentally, Iceberg changes that. We would very soon go into how, but then Iceberg came in and it created an open table format for analytical data sets. Doesn't matter if you have a petabyte, terabyte scale warehouse, or you could even have like tens and hundreds of GBs on a bare metal as well, and you could build your warehouse if your data is not that big. It's absolutely possible. Many, many instances, enterprises are doing it that way, right? So it brings in that flavor of SQL warehousing on open files. So that's why it has caught up so quickly with data engineers, right? So this is the famous diagram, and we would go very deep into this. So essentially, Iceberg is only a specification which talks about how to implement these three layers: my catalog, my metadata, and the data files, which are the real files which are coming in. So the catalog only keeps a track of the latest snapshot, which is placed in a file called a metadata file within the metadata layer. The metadata file points to manifest lists, which are individual snapshots of tables. And then manifest lists has manifest files, where each manifest file keeps track of the data files underneath and creates statistics information, stores statistics information in them, like what is the upper bound of the columns, what is the lower bound of the columns. So if you have a query that I want to have data from this store where sale of product A exceeded 100 but did not exceed, let's say, 300, then you could actually push that clause within your SQL query, and Iceberg would know that, okay, I need to go and scan only those data files where this operation is there. And all it needs to do is query the manifest file, and it would give back the data. So your query would become a lot faster. So manifest files, it's a list of data files with all these data file related statistics. Then you have a manifest list, which is the one-to-one mapping for a snapshot. Then you have a metadata file, which actually points to the current snapshot. And then you have a catalog. Now the difference between the Hive catalog and this catalog, Iceberg catalog, is Hive catalog kept the table name as a set of directories, while Iceberg keeps track of individual files. We'll go there again so that it decants and synthesizes a little bit easily. But then Iceberg actually helps you write these expressive SQL commands. with most of the ANSI SQL commands aligned with the SQL syntax. You can also do schema evolution. So if you change your tables, your old snapshot will not fail to return if you're firing a query. And you could do time travel based on a timestamp. So I could push in a timestamp and say, give me the state of my stored data, store sales data, maybe 7 days back. You could do all that very easily. So the whole goal is to have Iceberg as my open layer and then bring in my query engine. I could query with Spark and Trino and PyIceberg and PyArrow and DuckDB and Daft, whatever is available, whatever I'm feeling confident with, whether it's a SQL or whether it doesn't support SQL doesn't matter. That's the end goal. So again, going back to the structure, so the catalog, you see the catalog here, it actually points to the latest metadata file, and the metadata file actually have the table name which points to the correct location. So we would see how it looks like, but then this is how it appears. So in your metadata file, it would have a table and the current snapshot ID with it. The manifest list, it's the snapshot for a state of the table. And what a manifest list does is it has this list of manifest files. And then a manifest file keeps track of all the underlying data information. What is this? Where is this Parquet file located? What is the maximum value of column A? What is the minimum value of column A? So that if a query comes in, I could pass in this information, right? So my catalog, my metadata, and my data, 3 layers. And the metadata has in it 3 more sub-layers, my metadata file, my manifest list, and my manifest file. That's pretty much all Iceberg open table format is. So if you're doing a write, what exactly happens is you fire a query that I want to insert into this table. The query engine is again your choice. The query engine consults the catalog, gets the latest metadata file so that it knows which table to go through, and then it creates the data file, which is the data, and then the manifest list, and then the manifest file, the manifest list, and updates the metadata. So let's take this example. I'm doing an invoice details table. I'm creating it with a partition of order date. And you might already see that what it does is it creates a metadata file, but doesn't create anything else because no data has been created, right? So I don't need any manifest file because there's no data file. So if you fire this query, what would happen is on your disk or on your storage, you would get a folder called metadata. You would get a folder called data with nothing inside data. In metadata, you would have a JSON file. Now, if you want to do an insert into that table, what would happen is, see the snapshot has gone from S0 to S1 now. So now what would happen is a data file would get written, the manifest file would update with the statistics of the data file, there would be a manifest list which would host these manifest files, and then the metadata would be updated to S1. So now if you look at it, what would happen is, see the v1 metadata.json has become v2 metadata.json. And then of course you have a data which is partitioned by the timestamp, and a Parquet file has arrived. And I have my snap-start.avro, which is the manifest list, and an avro file which is the manifest file. So we saw creation, we saw an insert, this is an upsert or a merge. So now what happens is the snapshot gets updated to S2, the partition get again added with more partitions because there are more timestamps coming in. The manifest list and the manifest file also get updated, right? So eventually what would happen is you would have a v3 metadata, you would have a new snapshot, you would have a new manifest list, and then of course these 3 Parquet files in 2 different directories, right? When you're reading, it's just the opposite. So the query engine would consult the catalog to get the latest metadata file. it would track the current snapshot and the manifest list. The manifest file path would be retrieved, and then data would come back. Right? All these images I've taken from the book Apache Iceberg, the definitive guide, written by Alex Merced. Strongly recommend you go through it. Very, very good one. So read steps. And this is just an example of a time travel. So see, for read, we went to S0, S1, S2, and S2 was the current location. But here I wanted data from S1 as well. So now what happens is it goes through the other hoop and then goes through that one as well for time travel. So it selects a specific snapshot based on the timestamp, and the manifest file path is retrieved for that specific snapshot. Now, you might have already seen and understood that all this would give rise to a lot of small files. And in a open data lakehouse or even in a data lake, that's a big problem. The more files you have, the more file I/O, and it actually grows bigger very, very quick, right? So there are different techniques. So if you come from, let's say, a cloud background, Redshift has this PostgreSQL technique called vacuum. Of course, here the technique is called compaction because of these small file problems nowadays. And then what it does is it follows the old Hadoop principle of consolidating some of these files into a slightly larger file. 128 MB was Hadoop's recommendation, but then nowadays we do a lot of 100 MB files as well. I've also seen 50 MB, but then 100 MB files, and that actually would lessen your file I/O to a great extent. Now for Iceberg, it's very easy to do. You could actually automate the whole process as well if you want. So eventually what would happen is all these files would come into one slightly larger file or maybe moderately larger file. And then all these programming languages would normally have some way of doing it, right? So in Spark, you have this package called rewrite data files. It's part of the Iceberg actions package on PyIceberg, and you could do it. Every other language supports it nowadays. So now that we have understood the read-write pattern and the basic structure, I would just want to maybe spend like 5 minutes on COW and MOR, copy on write and merge on read. So these are the Iceberg. In fact, for any open table format, this is how rows get updated, right? So copy on write, what it does is it updates your data files, creates a new data file, which is the file 008.parquet with this updated information. And my update query was update catalog people set where ID equal to 3, right? So the row gets updated, a new file gets created, a new snapshot of the table gets created with this newer version of this data, which is the default thing. You still can change it, by the way. So essentially what happens is when I'm reading it, I don't need to do anything else. I have everything. I just need to point to the latest file, right? But then the problem is that takes time. This whole merge operation takes time. And then there are many workloads which does not want to wait for this kind of a delay. That's why this other thing has come in, which is called merge on read, where the append would happen very quickly, so the write would be very fast. But then for read, what you will have to do is there would be a new file created, which is called a delete file. And of course, there are two kinds of deletes. And then I have this one single record which got updated in a new data file. So I need to merge these two while I'm reading it. So it's very fast while I'm writing, but it takes a while it's reading. For COW, copy on write, it's just the other way around. It's slow to write, but very fast to read. Now deletes, just so that you know, there are two deletes, positional and equality. Positional deletes work on the position of the file that needs to be omitted or skipped. And for equality deletes, it's just the value. It takes a little while because you need to go through and read so that you read the data file and then you merge the whole operation. So now that we understand, I just wanted to spend like again 5 more minutes on how Kafka has come into the game, right? So Kafka is mostly constrained within the operational tracks, right? So I have all these microservices, and I would push some events to Kafka to store as a streaming data, and then pass it on to a different microservice. Some other consumer would read it, and then create this whole chain, right? So it works on the operational side of things. While Iceberg is purely an analytical construct. I have a lot of data on disk, on Hadoop, HDFS, or on cloud storage, and I want to run queries, big aggregation queries, which would give me, let's say, sales data for a specific geography for 3 quarters. I want to see the highest selling products in order, right? Now, the problem is the data that Kafka produces or Kafka stores is not compatible with the kind of storage that Iceberg has, which is columnar stores, right? Iceberg stores data in Parquet, while Kafka is a row-based storage, it's Avro. So first is you need to now convert your row-based records to columnar if you still want to use it as a source for your analytical data sources. Then comes the schema. So Kafka has a schema of its own, which is of course non-compatible with all these other schema the catalogs Iceberg produces, right? Now, can you write programs to do, you can of course write programs to do that, but then that becomes a little brittle, that takes its own maintenance cycle, etc., etc. So Confluent has come up with this product called Tableflow, where with the click of a button, what happens is your Kafka topic gets materialized as a Apache Iceberg table for you. And the internal plumbing of changing formats, compaction, making sure the small files are all merged is something which is taken care of by this product called Tableflow. So essentially what happens is the schema of your Kafka gets flattened and pushed into these Iceberg specific catalogs. So the Confluent schema can now be fed into an Iceberg catalog, be it Glue or Nessie or Polaris or Unity. And what you could do is you could have your, let's say, SAP and CRM data, and then you would have your Kafka topics appearing as Iceberg tables, and you would be able to join them through SQL queries or PyIceberg programs if you're an SQL hater, right? So essentially you build a data streaming platform, and your Kafka and Flink for stream processing, etc., create these very, very high quality, deduplicated real-time records, and you push it into Iceberg so that your query engines could come in and query. But at the same time, your operational applications can also work on it. So we take a break for 2 minutes. If you have any questions, and then I would just start again. If you have any questions. You will just speak a little louder.
A little louder. So one specific question that I have is, why has Iceberg taken the pole position when compared to Delta, Lake, or pruning? Right? So that's one question. And then the second question is, there's a lot of activity going on in Iceberg, adding capabilities, native capabilities into Iceberg, right? Now, going down the line, wouldn't that become also like a traditional IDE?
Yeah. Thank you. So 2 questions. One is why Iceberg has taken a pole position compared to Delta Lake and UD. And the second question is, lot of things happening with Iceberg, and I know this guy comes in with a lot of RDBMS experience. So his question is essentially, are we trying to rebuild RDBMS in a big way, in a like large scale. So let's break these answers down. So number one, the reason Iceberg has become so popular is because it was open from day zero, and there was no product. It was an Iceberg specification written by Ryan Blue. If you have heard him anywhere, Ryan Blue, very nice guy from Tabular. Now he's joined Databricks. So it was a specification, and you could take the specification and you could implement it your way. So PyIceberg has implemented it completely its own way by not even using a single SQL statement. I'll show you. It uses PyArrow for data exchange, which I think is going to be, you are going to hear about PyArrow, ADBC, etc., arrow flights in a big way in the coming years. But then it was a spec, unlike Delta and Hudi, where it was not a spec, it was an implementation, and then of course a lot of things were put on top of these frameworks. Delta, there was this common complaint, still a complaint, is that 30%, so the Delta Lake version of Databricks, and if you compare it with the open source Delta Lake, it's like 30% of what the Databricks Delta Lake is. Now, I have not verified it, to be honest. I keep on hearing it. So it still needs to, so the Databricks team would still need to push that confidence within Delta Lake that we are at par or something of that sort, so that Delta Lake adoption actually snowballs into something big. Of course, Databricks bought Tabular, so now there is even bigger confusion that now you have two open table formats. What is the roadmap? How do you see the future? So I think that has eaten away a little bit on the Delta Lake, definitely, because if I'm anxious about a product roadmap, I will not use it, as simple as that. Now, Hudi is a different kind of an example, very powerful construct. I think it needs a little bit of love from, just like Iceberg got a whole lot of love from Databricks and Snowflake and Apple and Netflix and AWS and whatnot. Hudi would need that love. It just could not develop into something way big. But you still remember Uber uses it like absolutely crazily. There are huge implementations of Hudi in Uber. AWS internally uses a lot of Hudi as well. But then what I've seen is AWS used to be the patron for Hudi for a long time. But now I see a lot of focus has shifted into Iceberg. Of course, because of popular demands, etc. I was with AWS as a principal architect for a long time. And I remember those days when Hudi used to be like come on top of Iceberg. So that might be one of the reasons why I see this has happened. Coming back to your next question, 100% right. It is an RDBMS all the way along. So what we are only creating is completely decoupled. As I told you, it's called composable architecture now. So all these layers are composable. So I mean, you look at it, can you change the B tree in PG-SQL? You can't. Can you change the read-write pattern in Iceberg? You can, technically. You can create a GitHub issue like in Apache Iceberg, and you can talk about and vote and then get your community around, create a voice, and then they would change it, right? So I think it is RDBMS, but in a far more modular and composable way. So, but it is an RDBMS. I mean, in RDBMS you have a table format, you have data files, you have buffer spaces, you have different search algorithms which is happening, and you have different ways of creating write-ahead logs and then compact it and get your data into materializing into files. There is no difference whatsoever. But in a very composable way, in a large manner, and so that the adoption becomes a lot bigger, and it does not remain proprietary. It does not remain proprietary. So today, my query, I can use PyIceberg and Daft and DuckDB and PyArrow. It's completely free. I can run it on my laptop. I can run it on my Office enterprise server. I can run it on a Azure VM or AWS EC2. I can run it on a Nutanix bare metal. Heck, why not? So the point is, this openness counts. I don't want to get locked in. You have never seen what is going to happen in days to come, right? So I think that's one of the reasons, and data and AI world is ever changing. There is this inherent anxiety. Even if everything is working well, you would think, what is going to happen? Would a LLM data engineer come in and just create completely new things? He will not, but then I'm just saying. So I think that's one of the reasons why it has come in. Please speak a little louder.
On the story, then, having any sort of that, Iceberg is solving a lot of problems. But with respect to engineering the Iceberg, what's the main problem that is solving over?
Yeah. So you would actually see, so Tableflow is a Confluent product, right? And now every single streaming storage provider, they're trying to bring in this Iceberg flavor, right? And the reason is to have an analytical estate of all these data warehouses, ODSs for banks and FSIs, and then different data stores. And then I have a data streaming platform, right? Where I have my Kafka topics and all those things, Flinks, stream processors. There is this friction that people don't want to maintain and keep both these. So while there would be streaming, and I don't think it would ever converge into a batch, the analytical part of it would require that my stream storage and my static storage, my data warehouses can be queryable at the same time. I think that's the primary design motive, that I am okay to have a 5 minutes delay, but I want my topic data to be materialized and showing up in my Iceberg table. So if you look at it, there are companies which run batch jobs which run for 9 hours. They start at 10 o'clock, end of business, and the next day the sales rep would come in, he or she would open his or her laptop at 9 o'clock and see that the batch job is still running, the data is not updated. So if you can bring it down to 5 minutes, you can think about the kind of possibilities it unlocks, right? Like Facebook, I mean, or LinkedIn, you post, nobody is liking it, there is no action, and then suddenly 3 days later you see 3,738 likes. I don't think you would like it, right? So it's a similar kind of philosophy. And you would see a lot of such implementation going around.
Optimization process and so optimization simply is basically considering small time to give a time.
Can you speak a little louder?
Is it better now?
Yes.
Yeah. So optimization is a process which basically considering small files and basically makes a serially for a given time. So in that case, do we end up losing the old snapshot files, or does it create a new snapshot for these particular things?
It does create new snapshot files. So the old snapshot files, you can choose to keep it or delete it. But then it would create new snapshot files. But remember, compaction is only one of the optimizations. There are 1,000 different. So there could be space filling curves for Iceberg, right? If you're aware of bin packing and different sort orders, does it ring a bell? A Z order nowadays. Although Z order came from spatial data like 20 years back, if you go back and read the research paper. So actually the whole thing came, if you have a map and if I want to get a good understanding of the contour, the research actually shows that you could write Z's all across the map and it actually gives you a good visualization of the contour of the terrain. So that's how Z order has come in. And Iceberg Z order is also one of the performance optimization, right? Now what has happened is these have become very easy to do. So for Iceberg, it's just one configuration. There is a field called sort order. You could choose Z order, you could choose bin packing, and that creates all this magic. Similarly with compaction, same things happen. Snapshot file purging is just one configuration. You could choose to keep it, you could choose to delete it, stuff like that. But remember, data warehouse is unlike an OLTP, right? So the source data is always there. What you create is analytical data. And you would see that data warehouses get purged very often as well. Because you might not need, it is not your GST server, right? Where you'll have to keep the data for 72 months. So yeah, and it's fairly simple to do with Iceberg. Just like in Hoodie as well. I must say, I mean, of course, this is an Iceberg talk, but then these are all applicable for. In fact, Hoodie supports even more sophisticated space filling curves for optimization, just for the sake of it. I'll take your question. I mean, we'll run out of time very quickly. But I remember, please keep your question in your back pocket. So, Iceberg, quickly recapping, it's a specification. It's not an implementation. But if you look at the Iceberg release file, it's all jar files. Now, I've been a Java programmer for 18 years. Of course, now I am a Pythonista, converted. It's my new religion. I don't talk about Java anymore. So for a Python data engineer, it's a big problem. And even bigger problem if I want to include these Iceberg, Airflow, or Dagstar jobs within my ML ops pipeline, my feedback loops, my data drift cycles, it's a hell of a job. But then it is an OTF, it has its own data catalog, etc., which is a good site. So the idea again was what? I would have an open catalog, I would have my own compute query engine, and then I would have Iceberg. It could be a clustered compute engine like Spark and Flink and Trino and all that, although all those three are JVM based. Or it could be something else which is purely Pythonic, Daft and Dask and Polars and PyIceberg and PyArrow, etc., right? So this was the vision. But the reality is, everywhere you see the same thing. A JVM clustered query engine talking to Iceberg, and that completely obfuscates the problems that a Python data engineer would have in terms of having a developer love that I would need to do this Python thing, right? So you got to admit that data engineering, 70%, maybe more, are all done through Python. Very important to have a Python developer to have his or her own development setup. I would want to do it on my own laptop first, and then I would move it to, let's say, all these production grade clusters and cloud and whatnot, right? And then this infamous, I think it's a lady's face. I wanted to have like a gender neutral, but then Py4j is a big issue, big problem. You're writing a Python program and suddenly you get like a null pointer exception or array index out of bounds, all these Java exceptions. Absolutely hate it. So that's the reality, right? So that is going to change when PyIceberg comes into picture, right? So Python data engineers of the world unite, and PyIceberg comes in, and what it does is it listens to your voice that I want to do a UV add, or I just want to do a pip install and then get go. I don't want a Docker Compose app which would slowly build 1,000 things and then crash with all this security and authentication and privilege issues and all that. And I want this thing to be integrated with NumPy and Pandas and PyArrow so that I could have all my MLOps and I could do data and AI all seamlessly with me, right? I could do it on VS Code or PyCharm. And then of course, if you want fluent Pythonic APIs, that's the best. No disrespect for SQL, but that's also something which I want, right? So PyIceberg is a Python implementation without any JVM whatsoever. It's a native Python PyIceberg port library for programmatically access all your tables and do create, update, delete, etc. It's evolving fast. So currently it is on version 0.9, looking towards 1.0, and it already supports all these. So most of these catalogs are supported. Most of these namespace and table DDL kind of operations are supported. It supports many different file schemes. You could do it on local file system on your laptop. You could do it on HDFS, all the cloud storage. It supports these file IO based functions. It supports schema natively. You could pass the schema along as a PyArrow memory structure, which is, I think, fantastic. absolutely blows my mind. You could just cross-reference between pandas and PyIceberg with PyArrow schema so that every single data that you show later is completely type-checked. It supports partitions, just like your Hive, etc. And then it supports predicate pushdown, so you could write a table scan and then ensure that I only select 3 columns, that too with this specific value, so all my Z orders are respected. And then I could convert these table scan results to a pandas data frame, to a polars data frame, to a DAF data frame. I could just write a DAF program and then throw it on Apache Raichaudhuri so that it runs distributed. All these things are possible. For write, MOR is still not supported. So we are hoping if you want to look at the 1.0 roadmap, you would see it's there. So except MOR, everything is supported. So merge on read is currently not supported. So all these writes happen on copy on write mode. The beauty is pip install iceberg. That's it. There is a CLI as well for common tasks. You could have JSON outputs on the console, and then you have support for all these tooling, inspection API. You could look at partitions, you could look at snapshot, you could look at manifest files and see what's in there, all programmatically. So you could build this MCP. So now you get this understanding that I could actually build an MCP server and open source, push it on GitHub, and then it could become my Iceberg tool. And then I could have my Azure GPT or let's say a Llama, which would talk to this MCP server, and I could actually start cracking on Iceberg. So all these features are actually an enabler for creating an MCP. And if you feel enthusiastic, you should create it yourself. And it has good integration till now with all this. Very, very common data engineering tools. So the goal is very simple. It's how simply we could get started, right? So all you need to do is you just need to create a YAML file with the name of the catalog. For this demo, I've created an SQL catalog, but you could have a REST or anything else, AWS glue-based catalog if you're on AWS, etc. And then I've created a disk-based data warehouse, which is this DW1. And then my catalog DB is an SQLite DB, which is kept under PyIceberg catalog. That's it. All now is needed is you load the catalog and you fire your PyArrow structures there. You could do upserts and writes and all that. So that's the goal. This is the Slack. I strongly encourage you to look at it. If possible, contribute, create issues on GitHub. Be a committer to move this ahead for Python data engineering purpose. Fairly well known now. And so this is also the code that I've kept on GitHub. So if you just want to take a picture, you can, if you have a laptop, you can do it right now. And that's it. So I would show you a demo. I think I have time of around 15 minutes, Ishika? 15 minutes, yeah? So I would show you a small demo, and then I'm open for questions as well. So we could have like a working demo if you have a question. So all you need to do is you need to go to this GitHub called Lakehouse Days, which I showed on the QR. You would have the code there. So, oh, it's so small. So what essentially happens is I have this .pyiceberg.yaml file you need to create so that your warehouse and your catalog URI is stored. And then what you do is you go to, you can do it on a notebook, but I just did it on a VS Code. So this is the code for writing it, right? So we could quickly go through it. So what essentially happens is you don't need to create anything. You just need to create one folder called DW1 because my PyIceberg has a warehouse named DW1. And then if you just browse through the code, so I load the catalog by reading from the YAML file, which is my catalog YAML. You could do a print catalog properties first, and if you're really running it, you should stop there because that would only create the data folder with nothing in it, the metadata folder, one metadata.json file, and nothing else, so that you could gradually see how it grows, right? And then I have created a schema, point of sale ID, total amount of sales through that POS machine, and the machine make. And then I created a partition. The partition is my POS ID. And then I created a namespace, which is an isolated container for all your tables, schemas, if you know what I mean. But I did not, I mean, they have wisely not chosen schema because that would have confused the hell out of all these database folks. So my namespace is POS NS, and my table identifier is POS sales. So POS sales is my table, and POS NS is my schema or the namespace. And then I create a first batch of records through PyArrow. So I've created like a dummy kind of data, 3 devices, 3 device IDs, and then you do an append or overwrite. You have 2 choices. Overwrite means no exception. Append means if you want to. Overwrite means no duplication. Append means the same record would keep on appending. And I created a pandas data frame out of it. Then I did an upsert. I just changed the Ingenico or mswipe with Pine Labs, and then I upserted the data with an upsert command. By the way, upsert is supported only from 0.9 PyIceberg. And then I did a pandas. It would give you how many rows got updated. And then you could do a select with Pine Labs, and it would show you a data. And then you could do a delete, and then delete would delete the data, right? So you could just go ahead and run it. Yeah, so the unique violation has happened. So let's delete all this. And this is my PyArrow catalog. Actually, I can show you another very neat thing. Wait. So if I now run it, so if you now go through the output, so this is my catalog property which got printed because I did a catalog.properties print. The first insert completed 3 records, Ingenico, Verifone, mswipe. And then I had an upsert where I only changed the WI86 from mswipe to Pine Labs. And then I did a select, which of course will not change anything on the metadata. And then I did a delete where Ingenico was deleted. Now if you go to this, your data folder, metadata folder, you have your metadata. So you have 3 metadata because 3 operations, create and then 2 operations. And then you have the snapshot files with snap. And then of course you have your data files, which is partitioned across these 3 POS IDs, point of sale IDs, 3 different parquets which have been written. Let me see if I already have it. Another cool thing which you could do is a very cool thing what you could do is I could actually do a duckdb, what was the command? Duckdb -ui, and I could actually do a PyIceberg catalog, PyArrow catalog.db. See? So what has happened is you now have your catalog which is also queryable through DuckDB. and you can actually fire this query and it would give you a response, and you could see that what the table namespace is and the metadata location. And since it's a SQL catalog, I could actually do it with DuckDB. And DuckDB UI is also now supported from the last version. I forgot what the last version was. So yeah, I mean, you could just go back and try it out at home when you have leisure. You just need to do a virtual environment so that you don't screw up your rest of your Python project setup. I've also uploaded a notebook there. If you're a notebook person, you could do everything on notebook. But yeah, so that's it. And if you have any questions, happy to take it. As we still have 10 minutes, so we can do it for 5 minutes. So I remember you had a question, so we could go back to you. We'll do it for 5 minutes and then let the next speaker set him up for like 5 minutes. Yes.
Yeah. So I just wanted to ask you, whenever you are able to try to make Iceberg in engineering, so why not use Apache Iceberg? Like Apache Iceberg being more for like writing data,
Well, I would argue on that. Apache Iceberg and Delta Lake also is very good for streaming writes. It's based on customer demands mostly. So the kind of customer requests and customer requirements come through has been mostly on Iceberg and Delta Lake. That's why Tableflow, to start with, has started with Iceberg, which is now GA, generally available. Now Tableflow with Delta Lake is coming in this quarter. And then Hoodie, let's see if there is considerable demand. Definitely there would be a chance to hook it up with it. Yeah. Yeah, sure.
What's your perspective on almost that?
Yeah. So his question is, PyIceberg as a purpose-built compute. How do I see it compete with, let's say, Trino, Spark, etc., and how does it move forward? So I think, and it's not only me. This whole small data revolution has come in, right? With Jordan Tigani doing the DuckDB pitch 2 years back. I don't know if you followed in 2024, there was a small data world, like a big data world in San Francisco. 5,500 people came in there. 95% of customers or enterprises which those developers and engineers represented had less than 50 GB of their data platform size. I'm not saying that your enterprise would have 100 GB size. It might have 500 petabytes as well. But then I think the rise of such compute or query is driven by the fact that not everybody needs a cluster. I might not need a cluster. I might have my data on S3, but it's not big enough. I don't need Spark. I don't need Trino. I can just have one EC2 VM run there, and then I could run this PyIceberg program and it would get me my data. I think that's a fundamental shift that's happening, which is the rise of Daft and DuckDB. Look at DuckDB's funding that they have been getting for their company Mother Duck. It's amazing. So small data is a phenomenon which you got to accept. I'm not saying big data is dead. So Jordan has written that famous post called "Big Data is Dead, Long Live Big Data," but I don't think it's dead. But then not everybody has big data. Uber would have big data, Ola would have big data, Amazon would have big data, Apple, Netflix would have big data. But let's say Starbucks, they will not have big data. Chai Point, they will not have big data. But don't you think they need analytics and all these predictive analytics capabilities? Hell yeah. So the point is, we should have that choice whether I want to go with a clustered setup or not. And PyIceberg is one of those movements which gives you that choice from a Python data engineer's perspective. Perfect. So if you have no more questions, I will stop it and then I'll be around. And oh, you have one more question, okay? Sorry, please speak a little louder.
Can you talk about field partitioning
Iceberg, yeah. So of course I omitted that because otherwise the talk would have been very bloated. So you saw how I partitioned my, please have a seat, yeah. You saw how my demo had a partition of POS ID, right? Points of sale device ID. Now, if you don't give that partition, and if you have, let's say, a timestamp kind of a field, Iceberg is intelligent enough to create something known as a hidden partition based on that timestamp field. Iceberg has that feature. But then, whether you use it or not is up to you, your discretion. You would mostly see that there is a partition field which is mostly provided by which you want to partition your data. And so hidden partitioning is also a very, very useful and powerful feature which you don't really get in out of the box in Hive. So in Hive, you have to have your folders as your one-to-one mapping of your partition. Now Iceberg actually lets you come around that and have this hidden partition feature where it can intelligently guess what should be your partition spec. So I'll be around. If you have any more questions, we can have a chat later on. Thank you very much.